Let's talk about 5.4, the beginning, some basic properties of definite integrals. Honestly, we've already talked about most of these in previous sections, either formally, like the first two. Also, make sure you get the dx's. I accidentally omitted some dx's on the first two and the last two properties. Those dx's should definitely be there. So we've talked about these before, either formally or informally, so I'm not going to spend a lot of time going over them. So the definite integral from a to a of f of x dx is 0. If you switch the limits of integration, you get the opposite result. You can take a definite integral term by term, and I was kind of already using these, even these last three, we were already kind of using these in the last section. If you have a constant multiple, you can bring that out in front of your definite integral. And then the last one essentially says that if you have, for example, let me just do at least a quick sketch of this last one. Nice little visual here. So, if you have some function, let's say, here's my f of x, and suppose we're initially looking at the definite integral from a to b. If you have some value of c in that definite integral, you could think about the definite integral from a to c would be, if we were thinking about this nice area example here where it's above the x-axis, so we would have, that would be the definite integral from a to c, and then if I had the integral from c to b of f of x dx, that would be this area. So visually you can kind of see, oh yeah, that would equal, the sum of those two areas. That would be represented by the definite integral from a to b. So, if you have a nice continuous function like that, you could kind of partition your definite integral into different regions or put it back together as one definite integral. All right, so let's jump in and just do a couple of examples with these integrals. Again, we've already kind of been using some of these properties, but these will be just a little more symbolic in nature. So we start off here, we're given an example 1, we're given a definite integral from 3 to 7 of f of x is 8. The definite integral from 7 to 10, excuse me, of that same function. So it's kind of key here. These are of the same function. And we're being asked something about the definite integral from 10 to 3 of that same function. So first of all, the integral from 10 to 3 of f of x dx, if we switch our limits of integration, we get the opposite result. And then we can see that we are given, kind of applying that last property that we have up above, we are given the integral from 3 to 7 of f of x dx. And if I add that to the integral from 7 to 10, so the second integral picks up right where the first one leaves off, then we can, that would become the integral, that would equal the integral from 3 to 10. So this is what we are given from 3 to 7. That was 8. The integral from 7 to 10 was 5. So this result ends up being negative 13. All right, let's look at another example here. So number 2, I'm given some definite integrals. Again, what's important to notice on this one is I'm given the definite integral from 1 to 3 of f of x dx, the definite integral from 1 to 3 of g of x dx, and then I'm also given the integral from 1 to 3 of h of x dx. So this time the functions are different, but they're all about the definite integral from 1 to 3. And now I'm looking for a definite integral from 1 to 3 of a combination, a linear combination of those prior given integrals. So we have a property that says up above, essentially, I'm going to just phrase it as you can take a definite integral term by term. So much like you took antiderivatives term by term, you can take definite integrals term by term as well. So let's first just kind of rewrite this expanded form here. And now, just like with your antiderivatives, with definite integrals, you can factor out a constant multiple. So a constant multiple can just get carried along, just like with your antiderivatives. The same is true with our definite integrals here. And now we have this broke down, and we've isolated for the 3 definite integrals that were given to us. So we're going to have 3 times the definite integral from 1 to 3 of h of x was 8 2/3. So let's just write that as 26/3, a little easier to work with. Minus 2 times the integral from 1 to 3 of g of x was 4. And then plus 4 times the integral from 1 to 3 of f of x was 2. So it looks like the last 2 terms are going to end up giving us 0. In the first term there, the 3's reduce, and so our final answer here would be 26. All right, one more example here using some of these properties. On this example, we have a piecewise function. So maybe let's even start with just a little sketch of this piecewise function here. So this won't be perfect, but a real rough sketch. So from -3 to 1, we have -3, -2, -1, 0, 1, and 2. Okay, so from -3 to 1, we're sine of pi over 2x. So the pi over 2, remember that's going to be when you have a constant multiple inside the function, that affects the horizontal stretching and compressing. So let's just like plot a few values here. So sine at -3 pi over 2 would be up here at -1. Sine at 2 pi over 2 would be sine of pi. That would be 0. And then sine at -1 times pi over 2, so sine at negative pi over 2, that would be down here at -1. Sine of 0 is 0. Sine at pi over 2 is 1. So it should, look a little smooth like a sine curve would, but it would look something like this. All right, but it actually starts right here and stops right, doesn't stop right there. Technically, that point is not defined yet, so that would start off here as a open circle. Okay, then between 1 and 2, we just have the curve 1 over x. So if you think about at 2, you'd have a half. So at 2, you would be right here at a half. And at 1, you are at 1. So I can kind of fill in that circle now because it's defined in the second part. So it's this, it's the full, kind of think about that hyperbolic shape in the first quadrant, but just that little portion of it. So essentially, we're looking at the definite integral going from -3 all the way over to 2. And so we're going to really look at breaking this into, of course, there's different, if we were to think about these areas, of course, there's different areas here, and some of them are above the x-axis and some are below. But the first regions are all defined by that first function of the sine of pi over 2x. So this is our first function. Okay, so that's going to come from sine of pi over 2x. And then the last part is going to come from the 1 over x. So that's this last area, kind of this last part of the definite integral. So essentially, we're just going to break this up with our piecewise defined function into these different integrals. So this is going to equal the definite integral from -3 to 1 of, let's first just call it f of x dx, plus the integral from 1 to 2 of f of x dx. Okay, well, the integral from -3 to 1, that is the sine of the pi over 2 times x dx, and then plus the second function here is, the one that we're looking at is the integral from 1 to 2 of the 1 over x dx. All right, so that is from the second part. Now, as I'm doing this, I'm realizing I somewhat jumped the gun in being able to evaluate both of these by hand yet. We haven't, but this is a good lesson for us. We haven't yet talked about how to evaluate sine of a constant multiple of x. You know how to take the antiderivative of sine of just plain old x, the antiderivative of sine of x, that we can do. So that's the opposite of cosine x, negative cosine. But we haven't yet learned, like, how am I going to deal with this pi over 2 times x on the inside? So I'm going to say, let's find this integral. I'm going to add to my directions up here. And I'm going to say, let's do that using technology. So we'll say using our graphing calculator. So this will be a chance to do that with our graphing calculator. So in particular, this part right here. The second one we can actually evaluate by hand, though. The antiderivative of 1 over x, remember, was the natural log of the absolute value of x, evaluated between 2 and 1. And so that would have been natural log of 2 minus natural log of 1, which is 0. So this just ends up becoming the natural log of 2. But on our first one, we're going to have to utilize some technology here. So let's erase that little thing here. I'm going to see if I can remember how to pop that in. Okay. So let's go ahead, and I just forgot to put it in the directions. I had already entered this into our y1, so we could kind of quickly do it. So if you notice in y1, I already have our sine of pi x over 2, or pi over 2x. So let's go into our math menu, and we want to go down to number 9, the integral. And we're going to integrate from -3 to 1. And since I have this function stored in y1, I could actually just enter y1 here, but let's just enter it from scratch. So let's just do our sine of pi over 2 times x dx, and we'll hit enter. And so actually, we could have done this one by hand if I had been a little more mindful of making some observations here. My graph doesn't look so good. Let's look at the graph done correctly. What we actually have here is some symmetry of the areas, that the sum of the two areas above the x-axis are equal to the area below the x-axis. And so this area actually ends up becoming 0. So actually, in reality then, this area right back here, that area came out to be 0. So our final answer here is really going to just be the natural log of 2. So that is our final answer to this definite integral. So remember, the other way that you can evaluate a definite integral in your graphing calculator, once you're looking at the graph, is to go to second trace, which is the calculate menu, and you can go to number 7, which is the integral, and then it says left bound question mark, and so you would enter -3 and hit enter, and then right bound question mark, we would enter 1 and hit enter. And so here's where you see at the bottom, the one thing I don't like, on your graphing calculator, it'll show the integral symbol where it says f of x dx, and that's equal to 0. So this is a more accurate depiction, but you can see how those areas that are above the x-axis are going to be equal to the area that is below the x-axis, and that's how we ended up with 0 on that. All right, so that was a good example there to look at. I can get rid of that. Why doesn't that want to go away? I don't need this anymore. Okay, well, let's see. Try it here and maybe get rid of it over here. No, it doesn't want to go away. Go away, graphing calculator. Okay, there, sorry. All right, let's get back to this. Sorry about that. I just didn't need that graphing calculator there anymore. All right, so let's go ahead and just end this video. Let's look at one more little thing in this section, which is the bounds of a definite integral. All right, so essentially this is something that we were using when we were talking about upper and lower sums, or the circumscribed or the inscribed rectangles. I also kind of ended up using this idea when we were proving part of the fundamental theorem of calculus, the first part. So here's what I just want us to observe. These are the upper and lower bounds of a definite integral. So the definite integral is this beige area under the curve. That's what it gives us. So it certainly needs to be bounded between the inscribed and the circumscribed rectangle. So if I look at the min point, let's say is this, in this case, is this left bound. So that is the minimum point on this interval. And so if we find the area of this rectangle with a width of b minus a times a height of m, and in this case it came from the left endpoint, but it would be whatever the min value is, that obviously is a lower bound on the actual area. And an upper bound would come from wherever the max point is in that interval. It doesn't need to be a left or right endpoint. It could be a midpoint or somewhere in that interval. And so if we find that area, so this full area here, so we can see this area, again, has a width of b minus a, and its height comes from wherever that max value is. So let's look at an example and let's find these lower and upper bounds on the area for cosine x on the interval from negative pi over 6 to pi over 3. All right, so I maybe could have used my graphing calculator on this one, but let's go ahead and just sketch it by hand. So of course we know kind of what our cosine curve looks like and how it starts here. And so it has this symmetry about the y-axis. And so we have something that looks roughly like this. So this is up here at 1. And we're looking at it from, let's say, negative pi over 6, let's say, is about here. So maybe from this value here over to pi over 3. So let's say that's about here. All right, so this is our interval. And so as we look at this region here, we first are going to look at the lower bound. So our lower bound on this particular area is going to come from, in this example, the right endpoint. That's going to be the place of the lower bound. So we would have cosine of pi over 3, and then times the width. Well, the width of this interval is going to be pi over 3 minus the negative, so plus pi over 6. So if you think about just multiplying this by 2 over 2, we have 2 pi over 6 plus pi over 6, that's 3 pi over 6, which is pi over 2. And our cosine at pi over 3 is 1/2. So we're going to have 1/2 times pi over 2, and that's going to give us pi over 4. So pi over 4 is our lower bound for that area. Now, if we wanted to determine the upper bound, in this particular problem, our upper bound is going to come from the max value, which is up there at x equals 0 on the function. So our upper bound in this example is going to come from cosine of 0, again, times this same width, which we now know is pi over 2. And cosine of 0, of course, is 1. So we have our 1 times pi over 2. So the upper bound on the actual area is pi over 2. So we have pi over 2 square units as the upper bound and pi over 4 as the lower bound. Now, if we were going to determine the actual area, so now the actual area under the curve, so just my red dots there, that is our definite integral. So the definite integral from negative pi over 6 to pi over 3 of cosine of x dx. So the integral, or the antiderivative of cosine, is sine. So we have sine of x. Now we just need to evaluate between our limits of integration. So we're going to have sine at pi over 3. So our sine at pi over 3 is our square root of 3 over 2. And then minus our sine at negative pi over 6. And the sine at negative pi over 6 is actually that negative 1/2, because we're down in that fourth quadrant there. And so what we end up with is the square root of 3 plus 1 all divided by 2. And so that would be the actual area under the curve. And again, if we went to decimal approximations, we would see that that obviously falls in between the decimal approximations for pi over 4 and pi over 2. So I think we'll stop there for today, and next time when we come back, we'll take a look at the mean value theorem.